material, which natural material has the highest conductivity? Diamond. Around what value? Around 2000, right? So you should know that 1000 is a quite high number in terms of conductivity. One of the lowest conductivity is 1.01. Wood has 0.1. Something around between 0.1 to 0.5, depending on if you're talking about natural wood. If you're talking about natural wood, we covered an example that it depends where is your heat flux. If it is with the grain or perpendicular to the grain. If it is engineering wood, meaning you take the wood, you shred it, you blend it together, then it will become isotropic. Yes? So that those values are somewhere in between 0.1 to 0.5. And one we did not cover is the heat transfer coefficient. So did you see the values? I uploaded the notes. Did you see the value of H? So can someone help me? So heat transfer coefficient meaning this is pertaining to convection, which is outside the material into the medium. So medium's properties will matter. Yes? So what kind of fluids that you are aware of? Gases and liquids. Generally for gases, could you just check? I've included the values. I think it's third or fourth image. Means titled appropriately. So H for gas is what and H for fluid is what. But then you have to also tell me that for moving fluids, if you're doing forced convection, how high it can go, right? Because convection is something that would depend on velocity. If you don't agree with me, I'll show you an example by switching on the fan. It depends on velocity, right? Yes? So then, you tell me the value for stagnant case and non-stagnant case. So you must have the values.
2 to 25. 2 to 25 for free convection.
2 to 25. So for stagnant case,
2 to 25.
for free convection, for natural convection, 2 to
25.
25. For liquid it is
10 to
10
10.
to 1000.
10 to 1000. For forced convection, there will be induced mixing
25 to
25 to
250.
25 to
250.
250. And then this
20 to 50 to
50 to 20,000.
but it will go even higher depending on if you are going really crazy on the velocity. Yes? So these are some of the values. What are the units?
watt per meter square Celsius.
Watt per meter square second.
Celsius.
It is square Kelvin. And please note the extra m here. This is a common mistake with conductivity. It's watt per meter Kelvin. Yes. Okay. Now, with that, let's begin today's lecture. With very integral part of heat transfer known as mathematical modeling. So let's understand how we do mathematical modeling. Am I audible at the back? Should I put this? Mathematical modeling of heat conduction. Switch it off. Now can you hear me? Hello. Now it's good. So what comes to your mind when someone says mathematical modeling? You must have heard of it before. What comes to your mind? So let's say I want to devise, this is a coffee mug or some mug that you want to design. What would you want to keep in mind while designing?
Heat transfer should be less.
The heat transfer to the ambient should be less. Yes? So what properties of this mug would you want to keep in mind?
Thermal conductivity.
Thermal conductivity, what else? Huh? Area, okay. Cross-sectional area. Then other properties such as density, Cp. Yes? So as soon as you note down the properties of a material and want to put it in a framework, that process is called mathematical modeling. Right? So that is one part of mathematical modeling, that you have a framework in which you want to put the values and see what is the temperature map in the system, as we discussed in the first class, right? As a thermal engineer, you would want to have a space-time map of the temperature in this system. If you are someone interested in mass transfer, if you have a petri dish, you put sugar, and that sugar will diffuse, you would want to get the idea of concentration map in space and time. Yes? So what is our aim here, specifically here in this heat conduction problem, is to get a space-time, or sometimes it's also called spatio-temporal map of temperature in the system. Yes? And it's generally done by deriving something known as governing equations. Yes, have you heard of this term, governing equation? So, the mathematical framework is called as governing equation, in which this information sort of goes. Yes? But how do we devise this mathematical framework? Can you give me some example of governing equations that you've come across before? For example, Navier-Stokes equation. What else? Continuity equation. Yes? And there are many in other branches. So, in order to derive this governing equation, or in some sense invent it, we have to use something known as conservation principles. We have to start with the conservation principles. Of course, we have to start with the aim, what we want is the space-time map of temperature, and I'll keep coming back to it because during our derivation we'll get confused or we might get lost. And this will help us, this will be like our compass, that what do we actually want. So, any governing equation that you just mentioned is based on some conservation principles, or you might have heard of the term balance. So what does Navier-Stokes, for example, balance? Momentum. Continuity equation? Mass balance. Yes? And in mass transfer you will have mole balance, concentration balance, or something. That is also a form of mass balance. So we have to start with, we begin with conservation principle. What conservation principles do you think now we should begin with here? Conservation of energy. Do you all agree? Because energy is somehow dependent on our aim, temperature, right? So let's begin with heat conservation or heat balance. Now, if I have any material, just drawing a roughly rectangular material like this block or this wall. In this material, I want to get space-time map, and I want to apply heat balance. What would I write? What heat balance comes to your mind? What is heat conservation? Energy conservation by the way?
Energy cannot be created
nor destroyed. Energy cannot be created nor destroyed, meaning it can only go from one form to the other. Yes? Now, help me write that. So you have this material in which you are doing heat transfer. Let's say you have this Q dot going from here to here. Heat entering, heat
plus heat loss is equal to.
So there is some in and there is some out.
In is equal to out plus loss.
In is equal to out plus loss, or can I say that whatever energy has been accumulated here or depleted here has to do with in and out, plus if I had some heating element here or resistance wire which would have generated heat, or oppositely which might have depleted heat. So accumulation should be equal to in minus out plus generation or depletion. Either of it. Yes, you have a confusing expression. So how do we write it mathematically?
In terms of flux, heat flux.
No, but yes, we'll come to that. But what accumulation of what? Heat? So can I just write Q? Accumulation. We covered it in the last class, I think. How do we write accumulation? Accumulation is occurring over time, right? This is equal to in and out. What is this? Heat in or heat rate in?
Rate.
Heat rate in, right? Plus some generation. Okay. So this is going to be a principle, and let's begin with, let's get more specific and derive a 1D heat conduction equation for rectangular geometries i.e. that is Cartesian coordinates. Why do I say rectangular geometry Cartesian coordinates? Because the equation that you will derive will be only suitable for rectangular geometries. We'll then go to the cylindrical geometries, which is more apt for mug. But for now, if you are looking at something like this board or this wall, which is very planar geometry, and you want to use an equation, then you would use Cartesian coordinates, yes? Coordinates. Now I want to write all this for a rectangular geometry. So let me make a nice rectangular geometry. And now what we'll focus on is we'll take a small element. See, the idea will be now is to write this equation for an infinitesimal element, for a very small element. And then we'll say, if it is valid for a very small element, and if the thermal properties are uniform, then we can write for the entire wall or entire material. So we'll take a small element, and now since it's 1D, we'll take a small delta X element. Okay, and we'll write an equation for this, and by generality we'll say this equation is going to be valid here, so it's going to be valid everywhere. Okay, now let me draw the coordinates. This is y, this is x, and this is your x coordinate, this let's call it x, and this let's call it x plus delta x, and this is your z. So it's sort of very large in y and z. Okay. Then what do we have? So here we will talk about the accumulation of heat. So can I write this as Q at T plus delta T minus Q at T divided by delta T? This is the accumulation of heat. Now please tell me what is Q in and Q out here? Or Q dot in, Q dot out? So Q dot at x minus Q dot at x plus delta x plus generation. Let's call it generation. If it's going to be depletion, then automatically a negative sign will come. But by default, let's go by generation. Now, what is this term, generation term? Let's spend some time here. A generation term is this volumetric heating term. So let's call it Q gen, and it is a volume integral of E gen, this volumetric term, dx dy dz. So in order to get an idea for the generation term, what do we say? Everywhere, let's consider that heat is being generated. See, currently we are, I told you about the example of wall, these rectangular geometries, what I see here, this table, this wall. They currently don't have any heating element in them. But we are deriving a general equation. When I give you problems for wall and board or something like that, I'll take away the heating part out. Yes? But this is a general equation. So let's, in this rectangular geometry, if there was a heating element, then everywhere I would define a scalar field known as E gen dot, and this could be a function of x, y, and z. So your geometry is creating some or generating some heat, and it's varying in x, y, and z. But we are deriving a 1D heat conduction equation, and one of the assumptions implicit in this assumption is that variation in y and z direction is negligible compared to x. So a lot of variations are in x direction, y and z, the system doesn't vary much, or the temperature map doesn't vary much. So, under this assumption, can I simplify this further? And since my dx is going to be small element anyways, and it will not vary much because this dx is already small. So I'm already doing an integral in an infinitesimally small element. Del x is already very small. Right? So what I can do it before even putting the assumption is that I can get the delta x out, E gen, which could be a function of x, y, z as of now, dy, dz, and now I'll use this assumption here, and I'll say E gen is not a function of y and z. Variations in y and z are not significant. So what I'll get at the end, please tell me, under this assumption. So my q dot gen will be E gen dot into del x into del y, but it's an integral, no? So basically integral. Wow. So it will be some width or some depth and then width. So can I call it AC, cross section area? Yes? Okay. So now let's substitute this here. And then what do you get? The right hand side is q dot x minus q dot x plus delta x plus E gen dot into del x into AC. And the left hand side, now left hand side is this, okay, same. Now again, as I said, somewhere in the derivation we might get lost. So what do we need to do? Go back to our compass, our motivation. What is our motivation here? We want information on, or an equation on temperature. Do you see temperature here? As of now, you see left hand side has Q, right side has Q dot, and then this E gen. We don't see temperature, so how do we go from something like Q to temperature?
C. Specific heat.
We use the idea of sensible heat. We assume now further one more assumption, you can add it in your copy, I don't have the space to write, is that we'll assume that the material does not phase change. It's solid. So any heat that is given will raise or change the sensible component. Once we know that, we can write Q is equal to
CP delta T.
MCP delta T, right? So I'll write the reference and represent both. You have M Cp T plus delta T minus temperature at T divided by delta T is equal to, you can use Fourier's law here as well, but I'll come to that in a moment. I know many of you are already anticipating. But let's assume, make believe that we don't know any law. E gen del x AC. Yes? Now, do you have, can you help me out here? We want, yes, do you want to come in front and help us out? So, what do governing equations usually look like? Differential equations. Does it, as of now, look like differential equations? So, what do we need to do? We took a small element. Now, let's take it to really infinitesimally small limit. So, which limit do we take it to? Delta t to 0 and delta x to 0. Yes? So here you have delta x. You can divide the entire equation by delta x. But you need delta x. So if you do that, you'll have delta x here in the denominator, which will not help you. So we need to simplify it a bit more. One more step is needed. What should we do?
Density.
So mass can be written, this mass is for the entire block. Is it for the entire block? For the element?
For the element.
So we can write density into volume. What is the volume of the element? Delta x into AC. So density into delta x into AC, right? And now we can divide the entire equation by delta x into AC. Yes? Let's see what we get. I'll keep our A here. So I'll get rho Cp T at T plus delta T minus T at time T delta T is equal to Q dot x minus Q dot x plus delta x divided by delta x plus E gen dot, that's it, A delta C we have divided. Yes? Now again our aim is to get temperature. Now what you need to do is to find someone who can tell you this Q dot to temperature relation. Now we already know that this is going to be Fourier's law, right? So we can directly use Q dot is equal to minus K AC. Oh, by the way, there will be AC below. K AC dou T by dou x. If it is x, then it will become at x. If it is x plus delta x, it will become at x plus delta x. Now, whatever you have done here it's a crucial step, and I want you to notice this. Because if you understood this derivation, I mean, this is the same derivation what you do in mass transfer. And this idea, so remember how you started. You started from a conservation principles on a small element, and then you applied, or you are going to apply limits. But almost always, you will need help of experiments to close the deal. To get your final governing equation, you cannot just rely on conservation principles. You need something known as the constitutive laws. We covered it in the last class. What kind of constitutive laws you are aware of? Fourier's law here. Yes, if the same derivation, if I replace T with C, temperature with concentration, you would get your diffusion equation. I don't know if it's already been derived in mass transfer, but it will soon happen. But you'll need, instead of Fourier's law, you would have Fick's law. Have you heard? No, but it's very similar. You'll have Fick's law. In fluid mechanics, rate processes, what did you have? Hooke's law. No, not Hooke's law. something law of viscosity. Newton's law of viscosity. No? Yes? Didn't you use this to get your final Navier-Stokes equation? You needed information. So that's what I'm saying. There's a pattern here and you should recognize instead of mugging up the entire derivation. Whatever, if you learn this derivation, then you can derive your allied subjects equations as well. And in the future, we'll use the same process. So you start with conservation principles, apply it on a small element, and then you need help of constitutive laws. In this case, it was Fourier's law. And then it's quite easy to now deal with. So what you have is rho Cp, the same thing, I'm not going to write it. And then you have minus, so this minus will come here. This will become plus. So can I exchange them? So have k dou t by dou t at x plus delta x minus dou t by dou t at x. I've exchanged them because of the minus sign. Divided by delta x plus Eg dot. Yes? Now I can take the limit to delta t tending to 0 and delta x tending to 0. What will we get? I took k out because k is not x dependent. I'm currently taking k to be uniform, not varying in space. Okay, can I rub this?
Yes, sir. Why is it dou t by dou t?
Why have we taken?
The temperature element in the
Oh, sorry, this would be x. Yes, you're right. Dou t by dou x. Fourier's law is x. Okay, so now in that limit, what we'll get in the left side? Rho Cp, dou t by dou time is equal to, this thing will become k. What will it be? A higher derivative in time, in temperature. Dou square t by dou x square plus E gen dot. You can take this to the other side. What you get is your the 1D equation that you wanted. Again, if you're solving cases where there is no regeneration, this last term will be 0. So this is your 1D Cartesian heat equation. Yes? Now, a very important question. What have I done here? This alpha, what is the ratio of k by? What is this alpha called? Thermal diffusivity. What does it mean? When I said, what is this called? Many heads nodded in the way that we know what it is in thermal diffusivity. But that doesn't mean that you know it. Right? You just know the name of it. What does it mean?
It's the ratio of the conductor to storage.
I mean, that's written there. So let's write it. We'll have it. So conduction by
storage.
storage per unit volume, but that's a good way to put the denominator. What's your name? Okay, nice. So now, again, the question still remains, what does alpha mean? It is ratio of conduction to heat storage. What this ratio would mean ultimately?
Alpha is high, then that particular element will conduct heat more efficiently, then it will increase its temperature.
Yes. It's true, we are closer than what alpha means.
Like the amount of
If
heat.
you follow your reasoning, you will get to the answer.
Like the amount of heat penetration into the material.
Isn't that already taken care by K? See, K tells you how much conductive is the material, how it will spread the heat. Then you have K by rho Cp. See, rho Cp, Cp is, how did we get to the idea of Cp when we discussed in the first class? Cp is, what is Cp? Specific heat, amount of heat needed to raise the temperature by 1 degree or something. So now you have conductivity by that quantity, that heat storage per unit area.
And let's suppose there is a rod between two ends. So
Okay.
alpha tells at what temperature is at, how fast it reaches to the saturation.
What reaches?
The temperature gradient.
The temperature. So it's a spread of temperature gradient or spread of how fast your temperature will spread. Because now we have a governing equation in temperature. Yes? So if your alpha is high, if your alpha is really high, so you can also write this equation as, you can take this K on the other side. I can write this equation as 1 by alpha. So let me write this. So let's understand this thermal diffusivity concept. So I'm going to take your 1D heat equation and I'm going to take the limit of E gen tending to 0. So there is no heat generation for this illustration. And can I write this then? 1 by alpha, rho by dou t, del square t by dou. Now take the limits. If alpha tends to infinity, meaning you have a rod, as you said, you have a rod, you give the heat here. So this is, let's say this yellow color is at time instant t is equal to 0. You gave a heat or you gave a rising temperature suddenly. If alpha is infinity, what will happen? It will instantly travel. So if alpha is infinity, so can I say this in very informal language? Temperature will instantly spread. Yes? If alpha is close to 0, then it will take infinite time to spread. Yes? So you can write this into a sentence. Right. Another way to look at this, or this idea that if alpha is really high, then in a very short time, so let me give you an example, okay? Let's take the example of the rod. You have this rod, at time t is equal to 0, give some temperature at one end. After you waited a lot of time, your temperature sort of spread throughout the rod. If you give t tending to infinity, if you give long enough time, doesn't matter what your alpha is, you're going to get your steady state temperature. Meaning that this term will vanish eventually. So this temperature, how could you derive? You could just write. So solving this will give you the steady state temperature. But the intermediate dynamics, the transient dynamics, meaning the unsteady dynamics, will be governed by the entire equation. Yes? This takes care of the unsteady part. This takes care of the steady part or eventual part. Now, so if I take a material of high alpha or low alpha, what changes here? I mean, I'm ultimately going to the final steady state as I say.
Steady state will occur between.
So this transition will occur faster if I'm taking diamond versus if I'm taking wood. Right? If the rod is made of two materials. So this transition time will be shorter for higher alpha. But let me confuse you a bit by giving you the values of some of the materials. And then later we will resolve this confusion, but first one has to be confused. If you talk about materials like water and air, alpha for them, if you calculate K by rho Cp for them, it will be of order 10 to the power minus 6. What is the unit, by the way? K by rho Cp, let's calculate it. What is K? 1 meter per meter. Divided by rho Cp. Rho is
kg per meter.
Cp is, what is Cp? What is Cp?
Joule per kg Kelvin.
Joule per kg Kelvin. Were you visualizing or were you sleeping? Okay, so what do we get? kg cancels. This goes meter square. Watt is joule per second. So you get meter square per second. Same as diffusion coefficient, right? Same as kinematic viscosity also. They are very similar equations. Kinematic viscosity is dynamic viscosity by density. Now, if you take the value of this 10 to the power minus 6 meter square per second, and this is for air, it's slightly higher, it's roughly 10 to the power minus 5 meter square per second. If you would take diamond or wood, the maximum alpha that you will get is 10 to the power minus 3. The maximum alpha value that you will get in meter square per second is 10 to the power minus 3. So, does it appear to you that no alpha is large enough? That no alpha is large enough, all alphas are small. So, all heat transfer processes are unsteady.
It is just a relative value.
Relative to what? So, I'll give you something to think about. Would temperature spread faster if I made this rod smaller? If I made this rod you're shaking your head to be no, if I made this rod 1 kilometer long, here I gave 100 and the entire rod is at room temperature. It will take longer, naturally, right, to spread it.
To reach the other end.
To reach the other end or to spread throughout.
Yeah, the throughout time.
Right, so we are associating alpha with this time, right? I'm just saying in this way of explaining, we are only taking one picture into account. As you said, it's relative to the length of the material. Right, so we will see later when we introduce non-dimensionalization that these things, the geometry as well as the thermal properties have to be taken into account together. Okay, so that will come, but that sense of confusion you should get from dimensional values. So what I'm trying to convey here is, in short or in other words, is that operating in the dimensional frame of mind can be confusing. And this is one of the motivations for non-dimensionalizing the system. If you get only 20% of what I said, that's also fine, you'll cover. But some foreshadowing is important. Okay, now, it's done. Okay, we have just 5 minutes, so I'll just. Can we quickly derive the same equation for cylindrical geometry? since we are all experts at deriving equations now. This is also 1D heat conduction equation. We might not be able to cover fully, that's fine, we can take it up in the next class. But I don't have a prop with me, any cylindrical with me except this rod. But it will help if I have a hollow rod, because then it will help you understand cylindrical element, how it is different from a Cartesian element. Because it is fundamentally different. So now what should I do? Please help me out.
Conservation principle.
We apply conservation principle, but first we need first we need the relevance. What is the relevance of this cylindrical equation? So the relevance for Cartesian equation was for planar geometries like this wall and so on. For a cylindrical geometry, we'll get equation and we can use to solve materials like this. Yes? What else do we have? So any cylindrical material, okay? Or any wire. Heating wire examples, we can solve this in that. Okay. So that's your relevance. But first you need to have then a cylindrical geometry. What element will you take?
Along the length.
Will you take this?
This pillar.
Delta x? That will be inappropriate, right?
At this. Along the pillar.
So you will take this. Yes? And we're going to derive it 1D meaning in R. So we have an infinitesimally small cylindrical shell of thickness
dr.
of thickness delta R. Yes? So please tell me how do I write these equations? The first, we'll apply conservation of energy like before. So you have this cylindrical element, okay? So there is heat in and then there is heat out. So again you will write the same. T plus delta T minus Q at T by delta T is equal to Q dot at R minus Q dot at R plus delta R plus generation term. Now this is your homework that you should find E gen into whatever volume is your volume element. So this will be your 2 pi RL into delta R. A quick way to see this is that this is a shell, right? So you have 2 pi R into L and then delta R is your thickness. But you can also take an integral and show this, that at the leading order this is. Okay? So now, let's do it in the